my name is Alex Bixel. I'm a graduate student at the University of Arizona. I work with Daniel Apai in his Earth and Other Solar System group. That's a project funded by NASA's Exoplanet Nexus program. And today, I'm going to be talking about the bulk properties of Proxima Cyn b. So some background. In the months since the discovery, we've seen a lot of really in-depth and really insightful work done to treat this planet's atmosphere and potential habitability, orbital evolution, and even, as we've seen, prospects for characterization in the near future. And I'm sure we're going to hear a lot more about that today. But what I want to talk about, and it's a lot along the lines of what Stephen Kane just talked about, is what underlying assumptions do we have here about the planet's bulk properties? In particular, I want to know what can we observe and what can we not observationally constrain. So we can observe stellar properties and many of the orbital properties, but we don't know the inclination. And so, as we've heard, when you measure an RV signal, you're only given the mass projected along, basically, your line of sight. What we cannot directly observe is a rocky or terrestrial composition. We can't directly determine what the mass is, and we really don't have much of a constraint observationally on what the radius might be. I'm particularly concerned about the composition here. There's been a growing consensus of sort of bimodal distribution from 1 to 4 Earth radii, where you have, of course, planets like the Earth, small radius, higher density, but also larger planets with higher volatile and ice fractions, similar in composition to, but not necessarily as large as Neptune. And of course, that would have serious implications for the habitability, which brings us back to the theme of this session. So my general method is to place the observational constraints that we do have into a Bayesian framework, where I substitute the non-directly observable parameters with statistical priors based on previous work from planets for which, for example, we have combined transit and RV mass measurements or TTV mass measurements. So briefly, I have, there we go, occurrence rates from Kepler for the radius, mass-radius relationship to determine the mass. We don't really have any observational constraints on the inclination. I've assumed an isotropic distribution. And then we have composition as a function of radius. So I reference a pretty highly cited work by Leslie Rogers in 2015, who found that above about 1.6 Earth radii, you see a sharp drop-off in the number of planets which are dense enough to be explained by a rocky composition. So we feed all these priors and the observables into a Monte Carlo simulation from which we can extract posterior constraints on the mass, the radius, and the composition, which are not directly observable. So I'll direct your attention to the right panel here. This represents a posterior mass distribution for the actual mass of Proxima Cyn b. I've decomposed it into a blue shaded region representing a rocky population and a red shaded region representing a, I call it a sub-Neptune population, but basically with a large volatile component or perhaps ice fraction. And of course, we see that the rocky population dominates the posterior mass distribution, as we should expect for such a low mass planet. We can extract from our posterior distributions expectation values and 2 sigma confidence intervals for the mass and radius. Briefly, what I'll note here is, of course, the expectation value for the mass is a bit higher than the proposed measured so-called minimum mass, which we would expect, and also that the radius, as I mentioned, is not, even with these constraints taken into place, is not particularly well constrained. But I thought that these values might be of use to, in particular, modelers who are trying to understand the interior composition of this planet. We asked the question, is the planet rocky? We find that in our posterior distributions, about 90% of the cases, the planet does have a rocky composition. Bearing in mind that based on the scheme we're using, this work by Leslie Rogers in 2015 doesn't necessarily exclude very low radius population of volatile rich components. So I put that as an upper bound, but I imagine it's pretty close. So these are the results I published in February, but what I'd like to do is expand upon this work with a more recent result from the California Kepler survey. So we've seen a paper on the archive as of March, I think, which finds evidence for a dual peak distribution in the occurrence rates, centered around about 1.75 Earth radii. So this very straightforwardly lends itself to the interpretation that I've been discussing, which is that we have a low radius, more rocky population and a higher radius volatile population. In fact, if you were here on Tuesday, there was a talk by Owen Lamer, who presented a hydrodynamical model formulation which predicted that planets below 1.7 Earth radii would lose volatile atmospheres very early on in the lifetime of the star. So this is highly consistent with that. If we just take this as a hard boundary at 1.75, we get somewhat higher estimates for the expectation values for its mass and radius, and I think a much better constraint on the probability that it's actually a rocky planet as originally proposed in the discovery paper. That's about 95%. So I'll discuss the significance of these results. So for this target in particular, and I think we can all agree this is one of the most interesting targets we have, I've provided more robust constraints on the mass, radius, and composition than were originally available following discovery. In particular, I've calculated that it's about 95% likely that this planet does in fact have a composition comparable to that of the Earth. Then there's that 1 in 20 case. And I think that becomes that it could actually have a volatile component. I think that becomes important when you start expanding if we are able to push down our RV sensitivity and find more and more small-sized exoplanets in the habitable zones of nearby M-stars. What I have here is a plot of the chance that this planet is going to be rocky as a function of the measured m times the sine of the inclination, assuming all the other parameters stay about the same. And what we see, of course, is that it falls off with increasing mass, but also that it seems to be highly sensitive to where we draw this cutoff in our planet populations in the occurrence rates. To which radius does this transition correspond? So yeah, in particular, basically this. What I want to know is what are the underlying populations here? What do these constituent populations look like in a function of occurrence versus radius? It turns out if you have some pollution of the sub-Neptune population to lower radii, maybe 0.1 or 0.2, it doesn't significantly impact the results. But we could imagine that there's a very long tail here which could extend all the way down to about an Earth radius and could significantly increase the likelihood that we have a sub-Neptune masquerading as a 1.3 Earth mass planet. I also think it's important to understand the spread in the mass-radius relationship. I've borrowed this figure from the Weiss and Marcy paper in 2014, but I can also provide an anecdote. So in the past 4 weeks, we discovered a rocky planet with a density of 12 to 13 grams per cubic centimeter around the M-star in the habitable zone, LHS 1140b. We've also seen updated masses for the TRAPPIST-1 planets, which assigns to them densities which are consistent with a very significant water fraction, 50% to 100%. And so these are very similar systems in that they're both M-stars. They're both receiving about the same amount of insolation, and yet we have such a large spread in what these compositions can be, and that provides us a lot of uncertainty in what the radius is if we can't measure it directly. In general, I think that we could apply this method to, say, directly image exoplanets. If you know what planet this is, you know it's not a rocky planet, but we could imagine that we had seen something like this, and we only have an idea of what the luminosity is. That's a function of the radius as well as the albedo. In the solar system, even among solar system rocky planets, albedo is highly unconstrained. And so if we could get some sort of modeling prior constraints on what the albedo of a rocky planet is, or a volatile rich planet is, or colors, photometric colors as well, that combined with the spectra would give us a much better idea of what kind of targets we're actually looking at with missions like James Webb, but mainly HabEx, LUVAR. So in conclusion, I provided 2 sigma or 95% confidence interval constraints on the mass and radius of this planet. I've also provided an estimate of just how likely it is that this planet is in fact rocky, and I think it's fairly high, but of course, because there's such a high mass tail and a potential for low mass volatile rich planets, it's not 1. I think we need to do further work in particular to understand the underlying distribution of sub-Neptunes versus rocky-sized planets in radius space, and to understand what causes the spread of the mass-radius relationship. Can we control for factors such as stellar type or luminosity? And finally, I would generally encourage a more Bayesian approach, basically a more large-scale statistical approach to interpreting our results when we have planets with unobservable parameters, namely RV-detected and directly imaged planets. So with that, I'll take questions.
All right. Thank you, Alex. So yes, we have plenty of time for questions.
Oh, good.
Washington. I love the talk. I love your last sentence. I'm a big fan of Bayesian statistics. I just want to echo what Heiss said earlier, that in the case when we don't have data, like for this planet, like we don't know what its true mass is, and like we have very little directly observed properties, we want to use as many of the priors that we have available as possible. And so it would be awesome if we did combine the geometric probability with the studies that you showed of the mass-radius relations with the information that M dwarfs don't have giant planets. Look at actually the distribution of planet populations as a function of stellar mass and incorporate that into a Bayesian framework. I imagine this would give you even stronger constraints on the probability that it's rocky.
Right. So these are the occurrence rates I use for reference. And right, I haven't really thought specifically in terms of what populations appear around M dwarfs, and I think that would be important. But I do at least try to constrain the occurrence rates of radii.
That's awesome. I must have missed that. Awesome.
But yeah, no, it could be that basically we have this graph, and it's about 1 to 1. But this is not for M stars.
Right.
So of course, that's something important to consider as well.
Cool.
Any more questions? All right, well, if not, let's thank Alex again.